Okay, so if you are printing the notes off one at a time, you'll notice that this one is very long. And the reason that this one is so long is because we have to get the basics down, and then it is going to, we're going to apply the basic principles we learned today for the other families that we're going to talk about as the week goes along. So tomorrow we are going to do the properties lab, just like the other lab, where we use the vernier probes. If you want, if you don't have it already, we're going to use the same graphical analysis lab, so then you can use the Bluetooth temperature probes. Okay, so if you have the lab from the app from the KQ lab, it's the same one. Okay, where you connect it to your phone. So that's for tomorrow. I just wanted to remind you, in case you want to go home and use your Wi-Fi, you don't have data, whatever. Okay. So hydrocarbons are the simplest type of organic compounds. They contain hydrogen and carbon atoms only. So hydrocarbon, yeah. Are they polar or non-polar? So again, hopefully you're going to be able to look at, recognize the patterns. You're going to be less stressed about, do I have to do the change in electronegativity and that kind of stuff. When you have carbon and carbon, then if you have the same thing, then it's going to be 0 for sure. That's nonpolar. And carbon and hydrogen, their values are so similar that they are both nonpolar bonds. So what we're going to look at in this unit, instead of worrying about chemical formulas like NaCl, H2O and stuff like that, what we're actually going to focus more on is drawing. How are the atoms arranged? So the formula for organic compounds, many of them, is actually kind of useless. So last year we did molecular formula where you had to calculate the actual number of atoms. An empirical formula was the simplest ratio, and a compound that often contains carbon, hydrogen, and oxygen. So I love to use glucose or ribose sugar molecules. They have the same empirical formula. They do not have the same molecular formula because the way their atoms are arranged is very different. Okay? So that is going to, and that's why biochemistry, the first unit in grade 12 biology, sort of connects to this, because it's going to be the same idea. How are atoms arranged is going to become a little bit more important than what's the chemical formula. Okay? So there are two basic types of hydrocarbons, aliphatic and aromatic. Aliphatic hydrocarbons are basically like more than 3/4 of today's notes. They are carbon atoms. They can be bonded in with single, double, or triple bonds, saturated or unsaturated. They can be rings, they can be chains, they can be long chains, they can be short chains, they can be branch chains, anything. And then we're going to look at a class of hydrocarbons called aromatic. So the word aroma sort of, implies a smell. And often we're talking about like aromatherapy is like, smells nice. Aromatic hydrocarbons, which are based on a special molecule called benzene, smell so bad that if I opened a bottle in here, you guys would actually vomit. Like, it causes aspiration. It's a very, very, very toxic nonpolar solvent. So sometimes it's called an industrial solvent. If you work in a place where you have to deal with solvents in your adult life, which should not be now, you would have to wear like a hazmat suit You would have to wear goggles and seal it so that nothing could touch your skin or get inside your mucous membranes. Very, very toxic stuff. Chemically, why is it so important? Because it has a unique bond arrangement. So again, how are the atoms arranged, which creates a lot of stability. So we give it its own special class because it has this really unique structure. So we're going to look at the representations of benzene. Benzene always has 6 carbons with alternating double bonds. So as much as they're like a subclass of hydrocarbons, the stability makes it so their chemistry is so unique, they get their own heading, okay? So when we do organic chemistry, there is going to be some important ideas. And the first rule for organic chemistry is how long is the main chain? So sometimes we call this the parent chain. And we are counting always, we only ever care about how many carbons. So as we go through the different families, like alcohols, ethers, aldehydes, ketones, if you happen to print the one file, you would see those as the titles. Then we're going to change the ending to tell us, is it an alcohol? We're going to use the ending OL. Is it an aldehyde? We're going to use the ending AL. That'll give you the clue about what the family is. And then we are also going to add stuff to the chain. So what we'll do first is we'll do some simple ones that have only single bonds. We'll just look at how to count the number of carbons, how you can draw it, because there's different ways you can do that as well. You kind of decide what you like best. And then we'll start to change the chain a bit and add more stuff to it. Okay? So this, which is also on page 12 if you don't like my chart here, is the root. How long is the carbon chain? So if it's 1 carbon long, then we use meth. 2 is F, 3 is prop, 4 is bute, and then 5 is pent, like a pentagon. 6 is hex, like a hexagon. 7 is hept, like a heptagon. 8 is oct, like an octagon. So then these ones in the middle sort of make sense, right? So use what you know, and then the other ones you have to memorize, okay? So today, these roots, maybe you've never heard them before or whatever, we're going to use these roots for the entire unit. We're going to put stuff on the parent chain. So we are going to use these over and over and over again. So it's not even that you're going to, like, yes, you have to memorize them, but if you don't have them memorized, then, there's some bigger issues, okay? So the more that you practice these, then it'll sort of become like you do have it memorized. It won't be something you have to consciously do, okay? So we'll start with the most simple, which is alkanes. They only have carbon-carbon single bonds, which means they are saturated hydrocarbons, which also means they are relatively stable. So we are going to have a whole lesson on just reactions, but again, we're always going to think about naming and drawing, yes, but also what are the properties. So we talked yesterday about how single bonds are very strong because it's sort of like the end, right? Triple can do double, can do single, single's sort of the end. very difficult to break these unless you're actually burning them, like combustion. So again, this general formula is true, but really apart from this slide here, we're never going to be concerned with it again. But you can use this to check your answer if you want. So if you have 2 carbons here, then that means you would have 2 times 2, which is 4, plus 2, or 6 hydrogens. But we're not really going to focus on what the chemical formula is. We are going to focus on how it's arranged. Okay? So for single bonds only, then the ending would be ANE. So when there is no longer just single bonds, or we've added something to make a new family, that's when we're going to change the ending. Okay, so let's do some examples. So no branches, we're going to keep it as simple as possible. So let's say I ask you to draw butane. Okay, so you're looking at what does the but mean? 4 carbons. And what does the ANE mean? Single bond. So those meth, eth, prop, but, that pair and chain, we're always talking about the carbon atoms. Once we start adding hydrogens or nitrogens, whatever, those things are considered to be add-ons. Organic chemistry, again, does not mean the chemistry of growing something without a pesticide. No, it means the chemistry of carbon, okay? So how many carbons are there? There's 4, and they're single bonded to each other. So sometimes students actually like drawing better than naming, because you can kind of decide how you want your molecules to look. So but is 4. You have to make them connected to each other. That's the single bond part. But how many bonds should carbon have? How many valence electrons does it have? 4. So it has to have 4 bonds. None of these carbons have 4 bonds. Some of them in the middle here have 2, but the ones on the end only have 1. So what do we do? How do we fill up the bonds? The general class for this family is hydrocarbons. Hydrogens are sort of considered to be like filler. So you can add in hydrogens and write them out nicely. So we need 1, 2, 3. This one already has 2, so we just need 2. 1, 2, 3. Okay? All of the carbons are full. All of them are happy with 4. Let's write that down. There are other variations of this you can do. So your textbook really likes to use a form called condensed. So instead of writing it like this, they'll write C. And how many C's or how many H's are around this C? There's 3. How many around this one? 2. How many around this one? 2. How many around this one? 3. So you can see that it's condensed, like it literally takes up less space on your paper. So your textbook loves this. You could even draw it like this is considered to be condensed. since the hydrogens are considered to be filler, you could even just do tick like this. So 4, and then go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's considered to be the ticks are considered to be hydrogen because we're just filling in the carbon to have 4 bonds. Now, there's another way you can do this called the stick formula. If you are a Googler or a video watcher, then you might find that you see a lot of stick formulas. Those of you that took biology and gone into more complicated molecules like cholesterol that are bigger, they might have shown stick formulas. Sometimes people get obsessed and they're like, oh, I'm going to do the stick formula. You do not need to be a hero, okay? I don't look at your paper and be like, oh, they use the stick formula, extra marks. That's not a thing. You do what's best for you, okay? I don't care. As long as carbon has 4 bonds somehow, okay? So the stick formula, it is commonly used as you get more advanced because it's going to get rid of the filler, which is the hydrogens, and it's also going to try to show what happens when you put 2 tetrahedrons together, like 2 carbon atoms that are tetrahedral. You do get sort of a jagged zigzag shape. So each point is a carbon. So 1, 2, 3, 4. You don't need to draw this in, but I will show you, like, this is a carbon, this is a carbon, this is a carbon, this is a carbon. I do not expect you to do stick formula. I don't even think your textbook draws any really like this very much. Except when we do rings, which are kind of shapes, you'll be like, oh, that's way easier. But here, lots of people will do this. Once you start to do a bunch of these questions, lots of people like condense. Most people don't do this, right? We're all lazy chemists. That's a lot of writing, you know? Okay? So next there's another blank. So we're going to do you guys try these. See what you get. We want to make sure, I want you to know the meth, S, prop, whatever. So right now, if you need to look up what it is, great, look it up so that it starts to get into your brain, okay? Imagine that he got like an accident. Bad karma, don't say that. I paused. Okay, how many carbons does hex have? Good. So hexane is 6. So however you want to draw. 1, 2, 3, 4, 5, 6. Put in your ticks after. Okay? I'll do nonane. I'm going to do nonane in a condensed way. So nonane is definitely a weird one. How many carbons is known? 9? Good. do not need to draw it condensed like me. You can draw it out. But the one thing you can't do is this. Okay, do not leave it like this. That is incomplete, okay? Don't even write that down. Why is it incomplete? It does not have 4 bonds. So, like I said, sometimes students prefer to name or prefer to draw because you kind of get to control how it looks. So this is legit, but you're sort of at my mercy, right? I'm drawing this and you have to write the name. So you check. How many carbons does it have? 1, 2, 3. What's 3? Prop. And then you check. It has single bonds, so it's propane. Okay, wouldn't it be wonderful if things could be this simple, okay? All right, so now let's look at adding stuff. So this is technically called in your notes a prefix, like adding stuff before or to the root chain or the parent chain. Then sometimes you can have branches of carbon atoms and they'll be at right angles. So something like this. So it's obviously no longer just straight, okay? So this is important. This impacts the physical properties of a molecule. We talked a little bit yesterday about double bonds and being kinky. This is not a straight chain. It cannot lie together nicely. So in biology, you often talk about methylation and how that affects genes and stuff like that. So this is an example of where that comes into play, okay? So adding carbon groups, not in a straight chain at 90 degrees, is going to have a big impact on the molecule, okay? So we're still the number one rule is count the longest chain, and then we have to label what's left over, what the branch is. So the way that we do that, you count the number of carbons. But instead of using A and E, because that's reserved for the parent chain, we want to show that it's a branch. So then we use the ending YL. So this is a very simple example, but at first glance, what does it look like the longest chain is? How many carbons? Here. So you can't go like, you can't do that, right? It has to be longest continuous chain. So how long do you think that is? 4? Yeah? And then we have this branch left over, okay? So it's kind of like you could add them together. So we would still have 4, which is bute, and then 1, which is meth. So for a total of 5, 1, 2, 3, 4, 5. But we can't call it pentane because it's not in a straight line, okay? So the total's still the same, but we have to show that there's a branch. So when you go to do this, and again, when you like some of the questions in the textbook, they make them like super weird 90-degree angles. you just kind of have to do your best to find the longest chain, okay? So we could go 1, 2, 3, 4. We could go 1, 2, 3, 4, and then there would be one over here. That's still continuous. We could go 1, 2, 3, but that's only 3. That's no good. 4 is longer, okay? We're always going to find the longest chain. Actually, let's highlight that. And something else we can do, we're so used to going left to right because we're English readers. You can actually go right to left. So you could go 1, 2, 3, 4. 1, 2, 3, 4. And how do you decide which way to go? Okay? So eventually, we're going to talk about a few more things you can add, but you can see these here are bolded. These are like the golden rule of organic chemistry. Count the longest chain. If there's something attached, it has to be on the lowest numbered carbon. Okay, so I'm going to go back and take a look at this. So if I go this way, we agree it's 4. I agree, I like that. If this is my longest chain, if I start in the left, this would be carbon 1, this would be carbon 2, and this is carbon 3. And there's my branch. But if I go this way, right to left, which is not instinctually what we would want to do, where would the branch be? What carbon number is it on? It's on, this would be 1, 2. Okay? So I usually tell students, like students are, except in the weird ones in the textbook that like are wacky, look at where it's sort of like, you have to look where the molecule is busy, okay? It's busier on this side, so start counting from this side. If you go over here, it doesn't get busy for a while, right? You need the lowest number. So if we go left to right, this is 1, 2, 3. If we go right to left, 1, 2. So this is lower than this one. The convention is to put the parent last. It's like where the main action is, okay? The longest chain. If you wrote the parent first and the branch after, I wouldn't take marks off, but really try not to do that because your organic professor might. All right, so our longest chain is bute. And then our branch is what's left over. I'll use orange. How many carbons are in the branch? Remember, we only ever care about carbons. How many carbons? 1. What's 1? Meth. Good. And I don't want to write methane butane because I want to show the butane is the parent. So how do we show the difference? We use YL. You can leave spaces, you can use dashes, you can put them together. That's like chemistry grammar. You do you, okay? But we need to say where it is. So we decided what carbon was lowest? 2. So the branch is found on carbon number 2. That's why we write a 2. The meth tells you 1 carbon in the branch. The bute tells you that's the parent. And the ANE tells you single bond. if you were going to draw 2-methylbutane, like if I gave you the name and you drew it, you can draw it however you want to, okay? So you can draw it right to left or left to right. That's why some people like drawing better, because you kind of get to decide how you want it to look, right? You could even draw sticks. That's 2-methylbutane, okay? So usually students like to draw better because you get to sort of pick. But remember, please don't think that I'm going to, think better of you that you do stick formula. You do what makes you comfortable, okay? As long as carbon has 4 bonds. Yes. So you're good with this. This is the longest chain. So then we have to show what's left over. So what's left over is 1 carbon, which is meth, right? And then we use YL instead of ANE to show it's a branch and not the parent. Okay? So if there were 2 carbons, it would be ethyl. 3 carbons would be propyl. Okay? So you count the longest chain, which is going to be the ANE for now. Now, usually what happens is, because we always want the longest chain, methyl is a reasonable branch, ethyl. But once you start getting into propyl, then you can actually have longer chains. So that, you don't see a lot of propyls. You'll see a lot of methyls. You'll see a lot of ethyls. Okay? So again, the more practice you do, then even though it seems like gibberish right now, you'll notice that you'll see the sort of the same things over and over and over again. Okay? Okay, so some other things that we can add to the parent chain, and like I said yesterday, we can add halogens, and yes, halogens are generally polar, but they don't really have a big influence on the parent chain, so we don't give them their own family. We just sort of call them additions to the parent chain. And the convention, if you have a chlorine or a bromine, iodine, fluorine, instead of writing chlorine, we write chloro. Bromine, we write bromo. Iodine, we write iodo. If you wrote chlorine, the full word, I wouldn't take marks off. But just so when you see that, these 3 are most common. Iodine is very rare. It's a really big atom. And then you can also have NO2 added, and it's called nitro. So like nitroglycerin, trinitrotoluene, TNT. So we include this as one of the additions because it is commonly found in some pretty common organic molecules. Toxic and dangerous organic molecules, but nonetheless. Okay? So just as a summary, what are we going to do? We are going to, once you start adding stuff to the chain, functional groups, families, etc., then we have to indicate where the chain is. So first, you find the longest chain, then you count to the lowest number carbon. What are we adding? Is it a methyl, ethyl, bromo, chloro, whatever, nitro? And then you put the name together, okay? So let's do some more examples. Okay, let's do this one first, and then we'll see if it helps, okay? Okay, we can do the first one. All right, so first rule, count the longest chain. So you can go 1, 2, 3, 4, 5. When you count parent chains, let's say, do not draw this because it's not right. Let's say you call this a parent chain. All continuous, nice and aligned. Does this look easy to name? No, it does not, okay? So when you make a parent chain, it should make what's left over look reasonable. I can deal with these branches, okay? So you can go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So automatically that gets rid of the 1, 2, 3, 4, 5. But again, if you go 1, 2, 3, 4, 5, 6, then you've got this nasty thing over here. Don't do that to yourself, okay? We can go 1, 2, 3, 4, 5, 6. We can do that. 1, 2, 3, 4, 5, 6. You know what? Let's just do that. What you'll find is, especially when you're starting out, and I apologize for this, in your textbook, somebody might have done this. And the reason for that is, with their pencil, okay? The reason for that is because then you can see what the parent chain is, and then you can see what the branches are. Because you don't want to overcount, right? You're not going to go 1, 2, 3 as part of the branch, because this carbon is not part of the branch. It's part of our 6. So what is 6? How many carbons? Or what's the name for 6? Yes. Good? All single bonds, so it's hexane. Now it's up to you. Maybe your eyes are okay and you're like, okay, I can see the branches, or maybe you would like to further circle. You could do that. Okay, why did I do different colors? So one of the things that I forgot to say over here, it talks about alphabetically. So again, I am not going to be super particular about this, but 1 carbon, for example, is meth. 2 carbons is F, so S alphabetically comes before meth. But I won't take marks off for that, okay? So I circled them separately because this branch has 1 carbon, which is meth. This branch, how many carbons does it have? 2. As does this one, okay? So ethyl is alphabetically before methyl. So I'm going to write that down first. But we followed the first rule. We found the longest chain. What's the second rule? The lowest numbered carbon. Has nothing to do with alphabetical. We don't care, okay? So again, take a look at this molecule. Where is the busy side of the molecule? Is it on the left or the right? The right. There is much more going on this side of the molecule. So that's your clue. Okay, I got to start counting from the right. So this is going to be 1, 2, 3, 4, 5, 6. So where are the ethyl groups? There's an ethyl group on number 3. Is the other ethyl group on number 3? No, it's on number 4. So that's what these numbers tell us. Where is whatever, branch, chloro, whatever, nitro. Now, here's a really picky thing, okay? Technically, if there is more than one of them, you're supposed to go back to like the mono, di, tri, tetra, those prefixes, and it's like, oh my gosh, are you kidding me? But so what, if you wrote, actually, I'm going to use pink, sorry. technically you're supposed to write diethyl. If you forget to write the di, I will not take marks off. It is much more important that you write down the numbers 3, 4 because you're showing where the ethyls are. Okay? What's next? Where is the methyl? 2. And I left a giant space. I'll fix that. Technically, you're supposed to do alphabetical, but this year I will not take marks off. I cannot guarantee your organic prof won't. Okay? Do you have a question? You're okay? Yes. Yes. So we get the parent goes at the end. Yes. No. If you did, that's fine, but you don't have to. Just like we don't like carbon dioxide, we don't say monocarbon, chemists are lazy. Okay, so what's important? The longest chain, the lowest numbers, the di, if you forget that, that's okay. So if you get something nasty like this one, I recommend you go to the end. How many carbons are in the parent? 7. So make the 7 first. And now you are the chemistry person. So if you want to do left to right, great. If you want to do right to left, great. It doesn't matter. Okay? But once you start counting one way, you can't go back and forth. Okay? So it can be still helpful to count the carbons for yourself. So I'm going to call this 1, 2, 3, 4, 5, 6, 7. But you can go the other way. Now we're going to do bromo, which is Br. Where are the bromos? 5, 6, and 6. So I find carbon number 5. When there's only one thing, you can write it in the top or the bottom. That doesn't matter. But there are 2 of them on 6. You can't just write 5, 6. You have to write 5, 6, 6 because we need to know there are 2 on the 6. That's why it looks like that. That's not a typo, okay? Okay, keep traveling along. There's a chloro. Where's the chloro? Number 2. Again, okay, I'll put this one in the bottom because I did that bromo in the top. Doesn't matter. What's next? 3. Ethyl, that means 2 carbons. 1, 2, 3. Again, top or bottom, whatever. I've added everything. Now I'm going to go in and do my tick. Yes. You can write the hydrogens. You can even do a hybrid. Like you could put, some people will do this. They make the branches condensed, but then they go back in and do this. Whatever. Just make sure it has 4, okay? Yes. It's always got to be 1. From the left? So every bend is a carbon. Yeah, like the carbons in the middle here, is that the point? Oh, I went this way, right? 6? Oh, did I put on 5? Sorry. You're right, I did. There we go. Yes. Oh, like this? Or something? Yep, that's fine. Yep. No, because halogens only need one bond. So we're like following all the rules still. So when we get to oxygen, it'll either be a double bond or O and an H. Like it has to have two. Okay? Yeah. You would do like, just put them like sort of like never eat shredded wheat because it's four. Yes. Nope. I don't know why. Like I like it looks nicer kind of when the pointed the down, but it doesn't matter. Yes. Hold on, I can't hear him. Shh. Yes. No, I put try because there's three of them. If there's only one, you don't have to do that. No. Okay? All right. So alkanes are nonpolar. We already talked about that. They have weak intermolecular attractions. If you have nonpolar, what is the intermolecular attraction? Anyone remember? Yes. Wonderful. So as we get more complicated, then we're going to be looking for, can it be dipole, which makes it stronger, or the strongest, can it be hydrogen bonding, right? That's what we're looking for. The one thing, if you remember from grade 11, about, and the first unit, I guess, about intermolecular attractions is that the more atoms there are in the molecule, so sometimes, or in grade 11, we might have called that the molar mass, the bigger molar mass, then there is a greater amount of London dispersion forces possible. So if you did methane, which is one carbon, I'm going to leave out the hydrogens for a second, okay? Then it would only be one spot for London dispersion. Let's say you had oct, like in gasoline, 1, 2, 3, 4, 5, 6, 7, 8. How many spots would there be? And the easiest possible way to think of it is 8. Do you pump gasoline into your car? No, it's a liquid, right? And this is the reason why. Okay, so saying 8 spots for dispersion, that's really ridiculous, but we can just keep it really simple. 8 spots for dispersion forces, they're stronger. How many spots here? Actually, we can even just change this to 1. 1, we'll say 1 spot. We'll keep our diagram as simple as it possibly can be. So methane that comes out of our gas taps is a gas. It is not a liquid. And then we've already talked about this a few times. The single bond is not as strong, so it's not as reactive. Okay, so yes, we're going to move on, but we're going to build on what we've just done, okay? So, if you have a ring, we call that a cyclo. We put cyclo, but we're going to do the same thing. So, if you have prop, a ring of propane looks like this. This would be bute, cyclopentane, cyclohexane. I think this is ox. Yep. Sometimes cyclobutane's, like, I use the shape so it made a diamond, but it could be a square. One, two, three, four, five, six, seven, eight. So all you have to do is add cyclo. So this reactivity, this is very particular. They are more reactive because the carbon atoms are too close together. But usually there won't be questions quite that specific. The beauty with the ring, there's no beginning and no end, really. So this could be carbon 1, this could be carbon 1, this could be carbon 1, right? It's like the circle of life, no beginning and no end. So that can make them actually easier for naming. Usually I wouldn't ask you to draw something like cyclooctane. How nice is it for me to be able to use my shapes? You guys obviously can't do that. Usually cyclohexane would be the limit. Okay? So there are two real kinds of these that you can have. So you can have the ones that are all by themselves, or you could have ones like this. Do a square this time. Oops. So like I said, there's no beginning and no end, so that makes your life much, much easier. You can just call this methyl cyclobutane. And by default, it has to be on the first carbon. So you can write the 1 or not. You need the cyclo to show that it's not a chain, it's a ring. For this one, we have two things here. So you follow the same rules. Which one is the longest chain? The 3 or the 4? The 4. So butane is the parent. And so that means that this then becomes the branch. Okay, I can do this. What do we use for branches? We use YL. How many carbons in the branch? 1, 2, 3. But we need to say it's a ring, so we're going to put cyclo, propyl. No problem, just like before. And where is it? Number 2. Yes. Yes, sure. Let's think of it that way. Yes. Okay, so we can stop here. Now, what I want you to do